mention, I should. And there's a number of proofs of this, but this is Bianca's proof.
Just one thing. I think but this already has gone by. I think there was an X. I think it is X instead of C in the completion, right? Because some time ago there was a board or something that was written, but he already said forget about it because.
Okay. Probably. I think it should have been OX completion everywhere. I don't think OC should have appeared anywhere here.
And for somebody who might have want to see this recording in the future, I forgot to start recording before, so we'll have a piece of information missing.
Okay.
So it's not much, but yeah.
Just
so
a few minutes.
If you want, you can just quickly tell what you have done so far.
Okay. So let's see. So this is really, in a way, this is where things start, where it's important that before now, all I did was I mentioned that if you take a non-singular point on a surface and you take the strict transform of a curve going through it, then on the strict transform, the points, the multiplicity cannot go up, the order cannot go up. And I just indicated how you can use completion to reduce to the case of a blowing up of a point on the plane that we did last time. So this is really where it started. Okay. So let's look at the proof. Okay. So then let's take R as the maximum of the orders of points on C, the multiplicities. If R is equal to 1, then remember that means C is non-singular at P. But then C is in fact non-singular. So suppose that this R is bigger than 1. Okay, so let's go on from there. Okay, so then we can look at the set P and element is C such that P is equal to R is a subset of the singular locus of C, which is maybe I should say it's a proper subset of the singular locus, which is closed. So it is a finite, which is a finite set. It is a subset, it is a subset of the singular locus, which is finite. Okay, so you see in some of the things I'm saying here like this become very simple in a curve, and even if you go up to a surface or a threefold, like you could have curves in this maximal multiplicity locus and so on. So they get more complicated. Okay, so since C is a curve. Okay, maybe I should say the singular locus is a proper 3D closed subset of a curve. Okay, that's why it's finite. Okay, so the proof is by induction on R. Sending induction on R. Okay, so what we do is we construct a sequence of morphisms of morphisms like this. Which I'll call star. So we have, maybe it's finite, or maybe it goes in forever, goes on forever. Where, what are you doing? At each step, you blow up all the points which are in the maximal multiplicities locus. Each pi I is the blow up of all the points on the strict transform. Cn of C on maybe I should say pi n, Cn minus 1 of C on x minus 1, which have order R. So remember, we can never get a point which has multiplicity bigger than or. It's always less than or equal to R. So if it drops, okay, we're happy something's better. So the only thing we're really worried about is any sequence that we have of order R. And then the big problem is, well, if this is finite, then we've won. That we've reached a point where the order is, everything has order less than or equal to 1. But otherwise, what we have to do, we can go on forever. And then we look more carefully at the sequence. If this sequence is finite, then we have obtained that the B of Q Cn is less than or equal to R minus 1 for all Q. So we're done by induction. For Q and Cn, and we are done by induction. Okay, so then what if the sequence is infinite?
Just silly question. What does it mean to be the blow up of all the points?
Well, you can think of it as like a composition where there are these disjoint points, like maybe there's 2 for simplicity. You blow up one, and then you blow up the second one. So it's just a composite of it. But you can view that as being one morphism. So or even as one ideal, the product of the 2 ideal sheets. So okay, but it's just sort of you just blow up all the points, but you're doing it in a certain, you sort of ordered them. So like this. Okay, so okay, so we will assume then that the sequence R is infinite. In other words, no matter how much we blow up, we still have a point of multiplicity R. But then we will derive a contradiction. If it is then if it is infinite, then for all n in n, there is a natural okay z I guess it doesn't matter in this one, I guess. Points bigger and equal to 0. Okay, there's some, okay, this is very controversial about what the natural numbers are. So because of that, I'm writing this. Then for all n bigger and equal to 0, there are closed points. Pn in xn such that pi n Pn is equal to Pn minus 1. Okay, so we choose such a sequence that goes on forever. Maybe I should say Cn, in fact, such that, and the multiplicity on Cn is equal to 1. Okay, now, what one does is one lets R sub n be the local ring, O, xn, Pn, and then we take the completion. So then we have an infinite sequence of completions. Sequence of completions of local rings of blowups of points. Points like that. So this one I'll call double star. So this will be R0 into R1 into R2 and so on, going on like that forever. Okay, so now let's analyze how F changes along this this sequence. Okay, so let's suppose that X, Y are regular parameters and are not, and F equals 0 is a local equation of C in or not. Okay, so for instance, you can take a local equation of C in at the point E naught, and then take that equation in R naught. So now one sort of point here I want to make is that F is reduced. What does this mean? A product of distinct or non-associates of irreducibles. Okay, and this is necessary to have resolution. That F is an irreducible element, and this ring is a good ring. It's essentially a finite type over a field. So that means that when you take the completion, that something which is reduced stays reduced. Okay, but that the example which I mentioned in the beginning, where resolution fails, is an example by Nagata of a local ring where you can take an element local of a normal ring, in fact, where if you take the completion, then some element which was irreducible becomes the square of something. So it's not reduced anymore, and it's hopeless for resolving. Okay, so now that we're here, okay, so now after a linear change of variables, we in xy, we may assume that f0y is equal to the order of f0y is equal to r. In other words, this is a polynomial. f0y is some alpha times y to the r plus higher order terms. And this is because what you need to do is take that linear form, that a leading form, which is a homogeneous of degree r in x and y. And then since it's algebraically closed, you can make some change of variables so that you actually have y to the r as one of the terms. Okay, now by the next thing one pulls in is the Weierstrass preparation theorem. You have an expression with this assumption. You can write f is y to the r plus a1 of x, y to the r minus 1, plus arx, okay, where aix are series in k adjoint x. And of course, if you have a valued field and f is convergent relative to that valuation, including in the case of C, where the standard norm on C, that this can be these a sub i's are actually convergent. This was Weierstrass's theorem, but this is quite generally true. In fact, for any field K, that this is true. Okay, so and here where U is equal to a unit series. Also, I forgot to say that. Okay, so this is another one of the major tools in this subject. Okay, now we perform what Juncker initially called the Turnhouse transformation. Okay, and in fact, this is what Juncker initially called it, although later in life he realized that, well, Turnhouse did this, I don't know, maybe it was 1400 or something like that. He was an Austrian mathematician, I believe. And he used this to try to solve quintics and things like that, which of course was ill-fated. But if you learn how to solve, well, of course you learn quadratic equations, but cubic and quartic equations, you always start by making a transformation of this type. Okay, so this is where characteristic. Okay, because you want to be able to divide by r. And that if you're in characteristic p, you may be lost. Like this may be y to the p plus something, and then you can't divide by this. Okay, and then x, y bar are again regular parameters and are not.
But it's proof that you are representing by a Bianchi to working positive characteristic also.
Well, as long as p does not divide r.
Okay.
Because then see, you're lost, right? Because I mean, you have to divide by 0. So this is the restriction. So yeah, I mean, it would work. This part of the proof would work in characteristic p as long as p does not divide r. In regular not. And in fact, I think all of the reduction that we're doing will work in characteristic p, but with that critical assumption that p does not divide r. Okay, so and replacing y with y bar, we have an expression But in fact, I won't go through this, but since we're on a curve, there's sort of, you can sort of fiddle with this argument to make it work in characteristic P, but it won't work and you can't in higher dimensions, or not without significant modification. Okay, so we have an expression like this. And this is f is equal to y to the r plus a to x, y to the r minus 2 plus arx. Okay, and now since f is reduced, at least some case of I is not equal to 0, and then you set n to be equal to the minimum of the order of the series AIX over I. Okay, so I guess if it's 0, then the order is infinite. Okay, so we have this. We have n is bigger than or equal to 1 since the multiplicity is equal to r. That's in fact not a very difficult calculation, that you must have, since f is order I, that the order of ai x bigger than or equal to I for all I. Okay, but otherwise the multiplicity would be too small, the order would be too small. Okay, so I might comment that when he was young, that Abiancar gave this name to this transformation, but he found out later on in life that an Indian mathematician had discovered this around 800 or 900. So he wanted to change the name, and it was the mathematician's was Sridharacharya. And but unfortunately, it seems not to have caught on. But anyway, in my book, I tell the story, but I also called it a Chernhouse transformation. Okay, so now what can we do with this? And in fact, it's a remarkable fact that one can understand completely what's happening with the blowing up as you blow up from this representation of F. Okay, now let's look at the blow up then. This has regular parameters, remember, x1, y1, and we have two cases. The first case is x is equal to x1, y is equal to x1, y1 equals alpha, where alpha is something in our ground field. Or the second case is x is equal to x1, y1, well, y is equal to y. Okay, so in case 2, we substitute, we see y is y1 to the r. Remember in our analysis where f to bar is equal to 0 is a local equation of the strict transform. Then we solve, substituting into the f which I had erased, that this is equal to 1 plus a2 of x1, y1. Well, this is order bigger than or equal to 2, so you can divide out by y1 squared. And AR XR X1 Y1. And this one has order bigger than or equal to R, so you can divide out by Y1 to the R. And this will be something of the form 1 plus X1 times omega, where you can see X1 has to divide every one of those terms. So it's a unit. And so one can see from this that, in fact, the point P1 is not is not on the curve, right? Because F2 would have to vanish at the point. You set P1, you set X1 and equals 0, Y1 equal to 0, and you get 1. It doesn't vanish. Okay, so that's kind of the easy case. Now let's analyze case 1. Okay, this one is sort of vacuous. Okay, let's see what happens in case 1. So in particular, cannot occur. If remember, P1 is supposed to continue to have order R. Okay, so now let's do case 1. Okay, in this case, then remember using that method that we looked at before for controlling how things changed, where here F1 equals 0 is a local equation of the strict transform C1 at P1. Then now if you substitute in, and then you get this expression for this F1 bar, then this is equal to y1 plus alpha to the r plus a2 x1 squared times y1 plus alpha to the r minus 2, and then so on, other terms like this, like that. Okay, now this is where we make use of the fact that we have a missing term in here. There's no y1 plus alpha to the r minus 1 term. That was what we went to trouble to fix. And you see, because of that, one has that if alpha is not 0, the multiplicity has to drop. So less or equal to r minus 1. So if alpha not equal to 0, so one has VP1 C1 less or equal to r minus 1. The multiplicity has dropped. Okay, because the point is that if you expand this, one has that F1 griddle is equal to y1 to the r plus, I guess it's r alpha y1 to the r minus 1 plus, and of course, then next after this, there's some r minus 1 terms, but over here you can't get any y1 to the r minus 1 terms from this or lower terms. So since this coefficient is non-zero, the multiplicity has to be less or equal to r minus 1. Okay, so there's one remaining case we haven't looked at, and that is that's the case that alpha is equal to 0. Okay, so if alpha, finally, let's look at the case if alpha is equal to 0, and on top of that, we haven't had a drop, which is entirely possible. Multiplicity is still r. Then F1 continues to have the form that I unfortunately erased. Right? Remember, right in the beginning, we had this F, and the important property of the F was there was no yr to the r minus 1 term. Okay, well, if alpha is equal to 0, you see that's preserved. That if alpha is equal to 0, there's no y1 to the r minus 1 term. So we have it in that nice form of the turn transform. And if you look at that n, that calculation of n, it is decreased. You can easily see that it is decreased by 1, because this guy will have some order bigger than or equal to I, and then when you go through this this process, you see this one has to drop by 2, this one has to drop by r. Okay, so that means that in this n invariant, that's just, you're looking at the minimum of these orders, and then that has to drop. So somehow you found an invariant which allows you to finish it up. Okay, because now that you're back, really everything's in exactly the same form that you had in degree 0, except for the fact that that n has dropped by 1. So you keep doing it. So after at most n times, you have to resolve because n is always bigger than or equal to 1. Okay, so that's all there is to the proof. So for some I, which is at most n, we have that's an invariant. We have that pi as multiplicity less than r, which is a contradiction to the. This is supposed to have multiplicity r forever on ci, which is a contradiction. So this gives us the proof. Okay. We can resolve the strict transform of C after a finite number of blowups of the singular points. Okay, so that's the proof. Okay, so now, okay, so
this proof that you just presented, so resolve singularities on the non-singular surfaces.
on a curve, yeah.
So, but you said that at that point you used the characteristic 0, right?
Yeah.
Was it the only place?
In this proof, it's true, and in fact, actually, there's another proof which is also in my book where you use a slightly different invariant, where in fact you look at the Newton polygon and you measure, you have the order, the multiplicity, and you look at the slope of the Newton polygon, and using that you can show that in any characteristic that you can get the multiplicity to drop for a plane for a singularity.
And I assume that this type of proofs are something that you sort of can mimic in higher dimensions, and that's some sort of advantage, right?
That's right.
Because I assume that there are other proofs of curves that might be seen as simpler, I know, like normalization maybe, or
yeah, in some sense that's the simpler thing, simplest one, of course. If you believe in normal, well, if you know normalization, that does it right away.
Okay.
But it's, and in fact, actually, this Newton method for constructing the Brisou series, that actually really, you're actually constructing directly the normalization, or at least for a formal branch. But it's yeah, so there's all kinds of things work out, but you're absolutely right that in fact the ideas in this proof generalized to prove resolution in all dimensions, but of course, you know, it was just like a few blackboards here. The complexity gets enormously higher, but the idea goes through, and in fact, this is the idea which that Hironaka started with, and he ended up with proving everything that's possible for resolution in characteristic 0. So,
and also this proof using toric geometry by TC and somebody, it also works, of course, in all characteristics, right?
Yeah, you mean the one that
well, that he's trying to use
There's just something where he does this resolution for Bianca evaluations. Is that the
No,
one you're-
I mean, the origin that gave the idea for proving local uniformization that he has.
Yeah.
It is one that they use a toric geometry, right?
Yeah, that actually, that's, yeah, so actually there's a number of people that have looked at things, but in toric geometry itself, there's a fairly simple combinatorial argument that shows you can,
Singularity of curves, right?
that you can resolve any toric variety. That
Okay.
there's a fairly simple algorithm for that. In fact, even in the classic book by Mumford and Kempf and Sandona, maybe someone else, that they have an algorithm for that. So it's not so hard, but in toric geometry, initially you set up some dictionary.
Yeah.
And then after that, you draw pictures. So that's basically, they have various sort of subdivisions and so on, and then they get it. So you don't really see the algebra so clearly unless your intuition is very good connecting. Yeah.
Because I thought that was approved by TCA and somebody else, where they use resolution of toric varieties to prove resolution of any curve singularity.
Oh, I think that's right. Yeah, and in fact that's right. That can be done. That there is some this is the one where the point is you have to, if you take any curve singularity and if you embed it in appropriately in like a high dimensional projective space, or then which is a toric variety, then there's some toric blow-ups you can make which will resolve the singularity of the curve. So that's right. He does that. Maybe with Goldman, maybe that.
Yeah, there was somebody, I don't remember.
Yeah.
And maybe also something that might be interesting to mention, that I believe there's an advantage of this, is that you resolve the singularity keeping the same dimension of the embedded space, right? You're always doing it in another surface, right?
Right. Yeah.
I think there are proofs where you can resolve the singularity by taking a resolution in a much bigger space, right?
Right, which is, as you mentioned, is Bernard's philosophy. Yeah, that's right. And in fact, what I want to do is of course, as Jose points out, the point of this is that this idea does extend to prove resolution in all dimensions. But of course, it's hopeless for me to. I'm just going to say a little bit about that, but not much. But what I want to do is isolate here that what we actually did, what happened. Okay, so there was some very nice principle here. And this was something which is a wonderful thing about characteristic zero, which fails in general in characteristic B. Okay, and this is that in this proof. Remember, we made some change of variables to get this y, that in fact the non-singular it's a formal curve, which is the h, which is the vanishing locus of y, contained in the spec of OX P hat. I guess maybe it was a P naught, is a formal curve of maximal contact or C at P naught. Okay, so what does it mean? That means that if y is a sequence y to x is a sequence of blow-ups of points. Is a sequence of blow-ups of points. Above P of P naught, and Q, an element of the strict transform of let's see, or Y, and with P of Q of C bar is equal to R, and all that maps, and I of Q is equal to P naught. Then Q bar, this Q then is actually on H tilde, which is equal to the strict transform of H on Y. Okay, and this is, it remains non-singular. Okay, so this is what happened. So if you notice when we made that transformation to Y, that we saw that the multiplicity dropped everywhere except for in this one where the new equation was Y1 is Y over X. That's the strict transform of Y, and you keep iterating this. So this is the major principle, and it turns out that strict transforms that these hypersurface of maximal contacts always exist in characteristic 0, but they do not exist in characteristic P. Okay, so this is one of the things. But you see what happens in the general case is that, okay, a curve, it's once you've dealt with this case of codimension 1, points, you're just looking at points and things are pretty simple. You're basically done. We use that N invariant to keep track of what was going on. But in general, of course, it's much harder. But what one does is one can have some kind of induction thing. So you say, okay, so now we can get a reduction in the ambient space. That we have this, we're trying to resolve C in X, but this H has one dimension less. And we need to take some appropriate, slightly different resolution problem on H. But you see, we've made the significant step of dropping the induction. Okay, so I'm going to say a little bit more about the general case. Okay, so I'll call this some ideas about the general case. About resolution in arbitrary dimension. Okay, so in fact, it starts the same. We take W is a non-singular variety. And actually, one trick, which I could have showed you if we had a little more time, but I didn't. But there's a simple trick to reduce from resolution of an arbitrary subvariety to resolution of a hypersurface. You just take some kind of projection, generic projection to get this. So subvariety. Okay, so let's look at W is a so-called hypersurface. It's one dimension less. As I mentioned, you can reduce to that. And then locally, we have that V is the vanishing locus of F for some local equation F equals 0 of V in W. Okay, so when Hironaka does this, he he doesn't just resolve singularities, even though it's the first proof. What he does is he does the most general thing possible. So he has to look at these incredibly complicated ideals where you know very little about it, and he develops all kinds of complicated theory, like some theory of Grosvenor bases he independently developed, and you also use this concept of normal flatness, which he develops. But anyway, we're not going to go into that. And it's, in fact, the whole proof would have been dramatically easier if he had said, okay, there exists a resolution. I mean, he proves a lot more, because he proves you can resolve singularities by blowing up non-singular curves supported inside the variety. So that's a very nice and strong statement. But if you wanted the weaker statement, just saying there exists a resolution of singularities, you're not worried about what the map is, then you can do a trick to reduce to this case, and everything becomes much easier.
Silly questions. If you are to try to take the Hironaka's proof and consider a curve, would it be much simpler?
No, it would be terrible. In fact, in his introduction, he makes some vague comment about this, actually. I mean, it's not even clear how, I mean, of course, there's an induction, so maybe you can reduce a little bit, but it would really be an horrendous proof. So it's, and also be a little hard to separate it. But, you know, he's looking at all these terrible, these very complicated ideals with get through that. Okay, so it's, but then also another thing is that Hironaka's original paper is actually, he proves that where the base is a excellent local ring, but which of course that includes the case of a field, so it gives you everything in algebraic geometry, which is where people normally calculate it. But Temkin extended this to an arbitrary excellent scheme. In other words, it has a finite cover by excellent scheme. So that's of course is a nice and important generalization. Okay, so so I'll go on here. Okay, so now for Q and W, we define this order in the same way. This is the max n such that F is in MQN, which is subset of OWQ. With Hironaka uses the multiplicity, which is just this for a hypersurface, but it's a much more complicated thing if you have an arbitrary ideal. And now for Q and W, no, then I define this thing. The singular locus VR. This is going to be the set Q and W such that VQ of E is bigger than or equal to R. Okay, so this, in fact, if I for S and N, this is this. And in fact, this is a closed set. Zariski closed set. So this is a theorem. So you see, things get much more complicated than in the case of curves. You have to worry about this kind of thing. And this is because this function is what's called upper semi-continuous. This is a closed set. So what you can do is that you take R is equal to the maximum of these orders. Okay, and then you can say that this locus here, this is a closed set, right? Because there's nothing a bigger multiplicity. Okay, so then this, in fact, well, we already have this. Maybe it should write here that this is Q and W, such that we actually have VQ. V is actually equal to R. So that's a closed set. Okay, so Okay, so now what I'm going to do is give another definition of a hypersurface of maximal contact. Okay, so in this situation, that a non-singular codimension 1 some variety H and define neighborhood U of Q in W containing Q. I guess it's already containing Q. The hypersurface such that H contains Q. Maybe I should spell that out. But it's called a maximal, a hypersurface of maximal contact for V at Q. They have two properties. Well, the first one is that sing, the multiplicity, the closed set of the single points of multiplicity R, and you intersect it with U, and this is contained in X. Okay, that's the first case. So somehow that was there with the case for curves, but somehow since you only have one point, it wasn't quite so critical to put it this way. And I should have said H. That should have been an H. I just caught that. Okay, H. Okay, it should have been H. Okay, now what is the next step? The next step is this one, that if UN U1 to U is a sequence of blowups of non-singular subvarieties Fi of U sub I, which are contained in this closed set, and thing U by R. Okay, so this is equal to the multiplicity locus of the strict transform of multiplicity R on the strict transform I guess this should have been a VI, I guess. This should have been a transform of V on UI. Okay, so if one has such a sequence, then the strict transform HI of H on UI contains sing V R. Okay, so this is the analog of what this property we really discussed in for curves. And this one that was sort of there, we said, okay, the point had to be on the H, but now we have some big locus. So in fact, the way you define the thing, which is the method that Hironaka used was to use this Chernhouse transformation. So I'll just tell you how you define the thing, and I'll say a little bit at least about how you prove the two properties. And in fact, it's not very hard. That based on what we've done, you can prove it fairly easily, both the properties. Okay, so and this is really Hironaka's Avianker's theorem, which is that a formal hypersurface of maximal contact. Okay, so there are other methods besides this one using the Chernhouse to find one. In fact, Giraud has a very nice method using differential operators to find one, and this in fact gives you one which is algebraic. So in some ways it's even better. Okay, so let's suppose that Q is a point in this singular locus of the points of maximal multiplicity, and we proceed just like we did for the curve case. Let f equals 0 be a local equation of B at Q. And now if the methods extend, you take n plus 1 variables or regular parameters in OW. I'm calling it W. I hope I didn't call it X, the ambient space X before. I think, no, it is W. Okay, good. And OW Q. And okay, we can form the completion. We do this trick again. Okay, so then OWQ hat is for over an algebraically closed field of characteristic 0. It should remind you of this, and it's algebraically closed, I'm assuming. Okay, so then we can choose these regular parameters x1, xn to y, so that f is equal to some kind of a unit times y to the r plus summation I equals 1 to r ai x1, xn to y to the r minus I. This is just like for the case for curves. And then replace f. You can always do this. F over unit. And perform the Chernhausen and make a Chernhausen or Chernhouse transformation substituting again y minus a1 over r for y. Then we have that we have two facts here that we have that y f is this expression ai xn y to the r minus I. Again, the r minus 1 term is missing, and y is equal to 0 is a maybe I should say, and VH is equal to V of Y is a formal hypersurface of maximal contact. Okay, so that's a construction. And how does one prove this? The proof is not difficult. I think the proof is not difficult. The first case is case of one is just differentiating basically, and the proof of two of the second property is an expansion of our proof for curves. Okay, so basically what you can always do is choose the variables. So the thing you're blowing up, that's some subset of these equations here. We always have to have y, it turns out, because it's hypersurface of maximal contact. Remember the singular, the thing you're blowing up has to be contained in y equals 0. And then you can change these variables so that you add a few more of those variables to get y, to get the ideal. And then you make a substitution just like we did for curve, but there's a few more variables. So and it's really essentially the same analysis, only a little more complicated. Okay, so I'll just make a couple more comments that in fact Giraud had a nice argument for constructing in fact algebraic. He constructs algebraic hypersurface of maximal contact using using differential operators. Okay, again, this is in characteristic 0 and Narasimhan. And this is a student of Biancher, showed that hypersurfaces of maximal contact do not always exist, always exist, shall I say, in characteristic P. Okay, so this whole, and this is basically, I think, the reason why resolution of singularities is a theorem in characteristic 0 in all dimensions, and it's not in characteristic P because somehow everything you try in characteristic P, something like this happens. In characteristic 0, there's all kinds of miracles that happen, where all kinds of wonderful things go through, but the thing always collapses in characteristic P. So people, wherever anybody can actually prove anything, it boils down to making all kinds of complicated ad hoc methods where, you know, that this happens, you do this, that happens, you do that, and so on. Okay, well, I guess I've told a little of the story. So as you can see, there's to learn the general theory, there's a lot more to be done. And my book, for instance, I do have a complete curve proof and dimension in all dimensions in characteristic 0. And I also have a proof well, I have a proof for surfaces in characteristic 0 before that, but I also have a proof in characteristic P, which is due for surfaces, which is due to Biancher. And I also go through Zariski's proof of resolution of surface singularities using local uniformization. Okay, so I will stop here then. Does anyone have questions? And
Thank you, Fred.
yeah.
Other questions? Yes. And astronomy implies that there exists a finite number of lords, right?
Right, yeah.
And what about the number of lords?
Well, actually, for the third case, I gave an explicit bound because it's I had that invariant. I make these I get the local equation in a nice form, and then just by looking at these degrees of these coefficients, which are ai of x for the y sub r minus I and divided by I, and looking at their order, that gives a bound for the number of times I need to blow up. But unfortunately, it's not so simple. And in general, the whole thing gets kind of complicated because there isn't a set way to resolve. Is what happens. And in fact, in dimension 2, there's a so-called minimal resolution of singularities, which means that given a singular variety, there's a unique non-singular variety which dominates it, and such that if something else resolves, then you have then there's a map. Okay, so this is the so-called minimal resolution. So one can begin to ask questions like that. But it might be that if you blow up points, you don't get that. You might get something much bigger. Blow up points in curves, you'd have to in surfaces. And so it may be something else. You may have to blow up some strange ideal in order to do it. So and then when you get to dimension 3, then you completely lose everything because there is no minimal resolution of singularities. So for instance, there's a very beautiful example which is an example for a lot of things, which is if you take maybe let me write it geometrically. So I have to be sure I get the right number of equations. Okay, and this is, we can be in C4. Okay, so this is the 3-dimensional variety, and then I'll call this X. And now there's sort of 2 minimal resolutions. There's X1 over here, and this over here. This is the point P over here. In X1, there is the resolution okay, and this is I'll call this Y, and I'll call this X2. Okay, and this one over sorry, there should be a line here which is a P1, and this goes down. That's not a bad picture. Over here, there's also a P1 which goes down to P. Okay, but up here there's a P1 cross P1, which goes down here and goes down here. And the thing is that there's 2 rulings, where on this one over here, this is the exceptional surface which maps down to P. And you project onto one ruling to get this one, and you project on another ruling to get that one. Okay, so this one over here is, I believe, in fact, this is the blow up of the point to get this one. And then there are 2 surfaces in here, which one of them you blow up, and then you get the P1 comes in it. This is strange because and then there's another surface you blow up here, and then you get that gives you this other P1 there. So it's a very beautiful example. But of course, I'm pretty sure, and I realize someone asked me about about people who worked on these sort of programming these things. So of course, they'd be interested in this. And I realize I completely forgot until this moment to do that. But if you would write to me I would be very happy to look it up and tell you what it is. So maybe I should end by telling you my email address. Missouri. Okay, and then if you write to me about this or other questions, I'll be glad to write to you.
Before I open for more questions, there are two messages from the internet. The first one is by Von Welder. He says, thanks for the lectures. And the second is by Stephen. I cannot say, Lensito, I guess is her name. He says, thank you, Dr. Cutkosky. I really enjoyed the lectures and they reminded me a lot about the business, about quadratic transforms that Avianca used for local uniformization.
Okay. Yes, indeed, this is it. So this is talking about something else that Avianca did, as you can see. But yes, so Stephen, I had Stephen read this ramification theoretic methods book by Avianca. So he describes that there.
And this is the question in the complementation of what he asked. You said that there is for curves, you have like this bound. Is it sharp?
Yeah, yes, it is sharp. It is sharp.
Okay. More questions here? More questions from the internet? So I have a few questions, but I have to remember what else is going to ask. So here now about this business of positive versus zero characteristic. Is there some category that you could maybe try to say, okay, in this category, all these varieties here have hypersurfaces of minimal contact. First, are there such categories?
Well, if you're in small enough degree, yes.
Okay.
So in fact, this is how Avianca's proof of resolution in dimension 3 works. Okay. Is that there's a wonderful theorem by, I think it's Albanese, but it's some beautiful classical result, and it's described in Zariski's old book on algebraic surfaces. And the thing is that, and the proof works in any characteristic, is that you can, if you take a variety embedded in some big projective space, then you can find some kind of a projection so that it's becomes the projection itself. It's a birational map from the thing onto the projection, and at every point in the variety, the multiplicity is less than p. So that means that you can apply these hypersurface and maximal contact methods to that guy to resolve it.
So I guess the follow-up of the question to be in more or less how I asked it. So is the existence of minimal surfaces of minimal contact the only obstacle for resolution of singularities and positive characteristic, or are there other stuff?
Well, I mean, from a certain point of view, that you could say that's the only obstacle, because if it were true, then you'd be able to prove it.
Okay,
but then given the fact that it doesn't exist, and you run into all kinds of other problems.
So maybe I'll reformulate. If I have a category of varieties in which all these varieties admit hypersurfaces of maximal contact, could I expect to run the algorithm and
yeah? I mean, even in characteristic P, sometimes this can work. I mean, you can see the Chern-House. If the degree is not P of the equation, then the Chern-House is doomed to failure. But, sometimes you may even start with an equation where there's no degree or -1 term. But that's in characteristic P that for degree equations of degree P, that it's still a mess. There's other things that go wrong. But for instance, in the simplest thing is that if you take x to the p plus alpha to the p, there's no degree p-1 term. So that was the point, is that in characteristic 0, there's a degree p-1 term. That was the thing we made use of. But look what happens here. So in general, the fact that Frobenius is a homomorphism is that can be interpreted as one of the problems. And another interpretation of this is that essentially the binomial theorem fails. But one thing which you can say, there is sort of a general theorem that right now where everything is really stuck for going on is that we don't have embedded resolution in dimension 3. So we have embedded resolutions of surfaces, and in fact, that's to get this. I mean, there's several steps where to prove resolution dimension 3, he combines a number of classical methods, but one of the things he needs is this embedded resolution of surface singularities. And he gives a very complicated proof. And he himself said that was the main thing in this proof, was that he proved this embedded resolution of singularity. So there are other proofs like this, Kozar, Sato, and gosh, I can't remember their third author. It's a German mathematician that they proved this thing very generally, for certain. But the problem is that, see, with the methods he has, you could prove for that one that if you, you could prove quite a bit if you had embedded resolution in dimension 3. Then you could prove something like local uniformization in dimension 4 and characteristic bigger than 4 factorial. So that's so in fact the degree of this projection, I'm sorry, it's less than 3 factorial. That's what I should have said. That's the magic thing. So if you project something in dimension d down, that the singularities have order less than or equal to d factorial. That's what the method does. It's a very simple and beautiful method.
Any more questions?
I assume that there are no more questions from the internet either. So let's thank Dale again. And
Well, thank you.
is the recording?
Okay, thank you.